Bismillahirrahmanirrahim. Respected sir, Assalamu alaikum. My name is Muhammad Abdul Rahim. My ID is 009 and my department is PS Physics. Today I am here to represent my topic and my presentation topic is X-ray crystallography. Firstly, layout, definition, techniques, diffraction, methods, Bragg's law, principle, procedure, instruments, types, limitation, uses, advantages and disadvantages, applications, conclusion, and loss in references. Firstly, what is X-ray crystallography? X-ray crystallography is a method of determining the arrangement of atoms within a crystal in which a beam of X-rays strikes the crystal and causes a beam of light to spread into many specific directions from the angles and intensities of these diffracted beams. A crystallographer can produce a three-dimensional means 3D picture of the density of electrons within the crystal. By measuring the angles and intensities of these diffracted beams, a crystallographer produces three-dimensional picture of the density of electrons within the crystal. From this electron density, the mean position of the atoms in the crystal can be determined as well as their chemical bonds, their crystallography order, disorder, and various other information. X-ray crystallography has been fundamental in the development of many scientific fields. In the in the first in its first decades of use, this method determined the size of atoms, the lengths and types of chemical bonds, and the atomic scale differences among various materials, especially minerals and alloys. X-rays have wavelengths similar to size of atoms. They are useful to explore within crystals. In crystallography, the crystalline atoms cause a beam of incident X-ray diffract into many specific directions. X-ray crystallography can locate every atom in zeolite and aluminosilicate. Here is a diagram of X-ray crystallography. Here this is the X-ray source and this is a crystal and diffraction pattern generated by the crystals. Next is X-ray infrastructure. Here is the here is the diagram of X-ray infrastructure. And next is X-ray techniques. They are classified into three types or techniques. First, X-ray absorption method. Second, X-ray diffraction method. And third one is X-ray fluorescence method. Firstly, X-ray absorption method. In this method, a beam of X-ray is allowed to pass and the sample which is having the fraction of X-ray photons absorbed is considered to be a measure of the concentration of the absorbing substance. These methods are useful in the elemental analysis. Second one is X-ray diffraction method. These methods are based on the scattering of X-rays by crystals. This technique is helpful in identification of crystal structure of various solids. And last one is X-ray fluorescence method. In this method, X-rays are generated concentration in the sample and by measuring the wavelength and intensity of generating X-rays, one can perform quality and quantity analysis. And next is what is X-ray diffraction? Diffraction is a wave phenomena in which the apparent bending and spreading of waves when they meet an ob- obstruction. In crystals, the regularly spaced atoms act as natural gratings. Hence, the atoms of crystals are able to diffract X-ray. Mode of diffraction is different from different crystals due to vary in their interatomic and interplanar distances, and hence the diffracted rays produce unique pattern on radiographic films, which are fingerprints for every crystal. Hence, X-ray diffraction technique is a powerful tool for the qualitative study of crystals, as well as X-ray diffraction is based on constructive interference of monochromatic X-rays and a crystalline sample. These X-rays are generated by a cathode ray tube filter to produce monochromatic radiation, collimated to concentrate and directed toward the sample. A two diagram of X-ray diffraction. First one is a beam of light passed into a slit, and then uh, we see different patterns. Con- Means that constructive interference and as well as destructive interference. Here, two rays are reflecting on the plane, and they are reflected. Next one is X-ray diffraction. X-ray diffraction method. These are generally used for investigation the internal structures and crystal structures of various compounds. They are Law's photographic method, transmission method, black reflection method, rotating crystal method, powder method. These are the diffraction methods. And next is what is Bragg's law? Bragg's law states that when the X-ray is incident onto a crystal surface, its angle of incidence will reflect back with the sample angle of scattering when the path difference d is equal to a whole number n. Whole number represents by n of wavelength with occur constructive interference. Bragg derived the condition for constructive interference of the X-ray scattered from a set of parallel lattice planes. Bragg's law provides a condition for a plane wave to be diffracted by a family of lattice planes. The formula is that 2d sine theta is equal to n lambda, where d is lattice spacing, theta we know that angle between the wave vector of the incident plane wave, lambda is wavelength, n is in integers. Integers means 1, 2, 3, n integer. Bragg's equation, known as 2d sine theta is equal to n lambda, known as Bragg's equation. This equation is known as Bragg law, means uh, 2d sine theta is equal to n lambda, know that Bragg's law or Bragg's equation, named after W.H. Bragg and his son W.L. Bragg, who discovered this geometric relationship in 1912. Bragg's law relates the distance between two planes in a crystal and the angle of reflection to the X-ray wavelength. The X-rays that are diffracted of the crystal have to be in phase in order to signal. Only certain angles that satisfy the following condition will register. Sin theta is equal to n lambda over 2d. Main formula of Bragg's law is 2d sin theta is equal to n lambda. Sin theta one side equal to n lambda over 2d. This is a diagram. Incident X-rays. Two incident X-rays are fall on surface, and and the surface reflected the X-rays. These X-rays are reflected by the surface, and angle is theta 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 plus 2 theta is equal to 2 theta. And next is principle of X-ray crystallography. First principle is ray diffraction by crystals is a reflection of the periodicity crystal architecture, so that imperfection in the crystal lattice usually results in poor diffraction properties. A crystal can be described with the aid of grid or lattice, defined by three axes and angles between them. Along each third one is along each axis a point will be repeated as distances referred to as the unit cell constants labeled ABC, known as constants. Within the crystalline lattice, infinite sets of regularly spaced planes can be drawn through lattice points. And last one is these pin planes can be considered as a source of diffraction and are desi- designated by a set of three numbers known as Miller indices. And next is procedure. Procedure of X-ray. Following are the procedure of X-ray crystallography. Basically, first step or first step is the first and often most difficult step is to obtain an adequate crystal of material under study. The crystal should be sufficiently large, typically larger than 0.1 millimeter, known as millimeter, in all dimensions. All dimensions means three dimensions. Pure in composition and regular in structure, with no significant internal imperfections such as cracks or twinning. Researchers crystallize an atom or molecule because the precise position of each atom in a molecule can only be determined if the molecule is crystallized. If the molecule or atom is not in a crystallized form, the X-rays will diffract unpredictably and the data retrieved will be too difficult, if not possible, to understand. And next is second step. The crystal is placed in an intense beam of X-rays, usually of single wavelength. Single wavelength known as monochromatic. Monochromatic which has a single wavelength, producing the regular pattern of reflections. As the crystal is gradually rotated, previous reflections disappear and new ones appear. The intensity of every spot is recorded at every orientation of the crystal. Multiple data sets have to collected, with each set covering slightly more than half a containing tens of thousands of reflections. And next is the third step and the final step. In the third step and final step, these data are combined computationally with complementary chemical information to produce chemical information to produce and refine a model of the arrangement of atoms within the crystal. After the diffraction pattern is obtained, the data is then processed by a computer and the structure of the atom or molecule is deduced and visualized. And next is instrument components. These are instrument components used in X-ray diffraction. Generally, a typical X-ray diffraction contains below parts. First one is X-ray source, next is detector, third one is crystal on the end of mounting needle, fourth one is liquid nitrogen stream to keep crystal called. Fifth one is movable mount to rotate crystal, and last one is polymeter. Is the diagram of X-ray, primary X-ray optics, X-ray source, goniometer, sample holder, detector, diffraction beam, collimator. First one is X-ray tube, the source of X-ray tube. X-ray tube used as a source. Incident beam optics condition the X-ray beam before it hits the sample. Goniometer, the platform that holds and moves the sample optics, detector and tube. Receiving side optics condition the X-ray beam after it has encountered the sample. And last one is detector, count the number of X-rays scattered by the sample. And next is types of X-ray device used. Electrons are responsible for the diffraction and intensity in crystallography. Second one is electrons. They scatter X-rays weaker than heavy elements. And the third one is knowing this, protein crystallography use high intensity X-ray sources such as a rotating anode tube or a strong X-ray source of the analyzing the protein source. Is a diagram of X-ray tube rotating anode. Tung- Tungsten filament bearings high voltage, negative and positive. Filament supply, glass envelope, focusing cathode, X-rays. This, this is the diagram of X-ray tube rotating anode. And next is limitation. Limitation of X-rays. Small molecule crystallography typically involves crystals with fewer than 100 atoms in their S, S metric unit. Such crystal structures are usually so well resolved that the atoms can be designed as isolated blobs of electron density. Next one is, by contrast, macromolecular crystallography often involves tens of thousands, means 10,000 of atoms in the unit cell. Such crystal structures are generally less well resolved, more smoothed out. The atoms and chemical bonds appear as tubes of electron density rather than isolated systems. In general, small molecules are also easier to crystallize than macromolecules. However, X-ray crystallography has proven possible even for viruses with hundreds of thousands of atoms. These are the limitations of X-ray crystallography. Move on and uses of X-ray crystallography. First use of the X-ray crystallography is used to study many materials which form crystals like salts, metals, minerals, semiconductors, as well as various inorganic or organic and biological molecules. Second one is determine electron density. The main position of the atoms in the crystal, their chemical bonds, their disorder, and various other information. Third one is size of atoms, the length and types of chemical bonds, and the atomic scale differences among various materials, especially minerals and alloys. The method also revealed the structure and function of many biological molecules, including vitamins, drugs, proteins, and nucleic acids such as DNA. DNA known as deoxyribonucleic acid. And fourth one is characterizing the atomic structure of new materials and in discerning materials that appear similarly by other experiments. And last use of X-ray crystallography. X-ray crystal structures can also account for unusual electronic or elastic properties of a material, shed light on chemical interactions and processes, or serve as a basis for designing against disease. These are the uses of X-ray crystallography. And next is advantages and disadvantages of X-ray crystallography. Firstly, advantages. X-ray is the cheapest, the most convenient and widely used method. X-rays are not absorbed very much by air, so the specimen need not be in an evacuated chamber. And third advantage of provides high resolution information. And last one is unlike solution NMR does not require a protein be soluble in a high concentrated solution. And some disadvantages of X-ray crystallography. First one is they do not interact very strongly with lighter elements. Requires a protein crystal. Cannot be used with amyloid fibers. Fourth one is cannot be used very flexible molecules. And last one disadvantages crystal contacts can distort protein structure. These are the advantages and some disadvantages of X-ray crystallography. And now applications of X-ray crystallography. First application of X-ray crystallography is to determine atomic arrangement. Second one is to determine structural properties. Third one is to determine the catalytic activity of materials. Fourth one is to determine how a drug might interact with specific proteins and how the drug can be improved. Fifth one is to identify crystalline phases and orientation. And last application is to measure thickness of thin films and multi-layers. These are the applications. Next conclusion. Allow for the discovery of the structure of DNA. Allows researchers today to see how secondary protein structures in protein residues can fold depending on different environmental factors. And last is allows researchers today certain factors may affect protein structure. And now references. Thank you.